So welcome to this tutorial session on graph learning, principles, challenges, and open questions. So today we'll have two great speakers. So Ameya and Adrián. Yeah, so without further ado, so I'll pass the time to them.
Thanks for the introduction, and thanks everyone for showing up to the tutorial. My name is Ameya, and I'm a research scientist at Google Research, and this is my co-presenter, Adrián, who's a PhD student at Alicante. So today we'll walk you through a tutorial on graph learning, principles, challenges, and open directions. So we'll start out with some introductory material, some of the fundamentals around graph neural nets and graph methods in machine learning. And then we'll move to sort of more frontier topics based on what current research is about. And then toward the end, we'll have a nice panel discussion. So we'll have some distinguished panelists here. I'm sure it will be an exciting discussion. We'll get to hear a lot of hot takes. So make sure you don't miss that one. Okay, so we'll start out with an introduction. So I think most of you know what graphs are, but just for the sake of completeness, we have a set of nodes and some set of edges connecting various pairs of nodes. And you can represent a graph using an adjacency matrix that tells you which pairs of nodes are connected. Okay, and really when we say graph learning, we mean machine learning on graph structured data. So there's a wide variety of domains for which data naturally arises in a graph structure. For instance, molecular graphs, road network graphs, etc. And there are different types of tasks depending on what you want to predict. You can have node level classification or regression. You can have prediction tasks at the edge level as well, or the graph level. So things at edge level are, for instance, link prediction, where you want to predict whether two nodes are connected. Graph level tasks, you want to predict something for the entire graph as opposed to individual nodes. Okay, and really one of the success stories of the last decade has been deep learning, right? But if we kind of look at it, a lot of deep learning has been mainly on sequence data or grid data, right? So if you look at kind of convolutional neural nets, which were the rage back in the day and still used to some extent, they operate on grid graphs or grids of pixels. Similarly, transformers, they operate on sequences of tokens, right? On the other hand, graphs have much more general topological structures, and local neighborhoods can vary a lot in different graphs, right? There are sparse parts of the graph, there are dense parts. So, how do you even think about learning on graph data? So just to give you some intuition with the familiar convolutional network, what are some of the salient properties there? So the idea is here really we have a specific example of a graph, which is the grid graph. And you have a convolutional filter that pretty much convolves values of these different pixels. And you can think of it as convolving the nodes that are within a certain k-hop neighborhood, right, in this grid graph. And because the filter is something small that doesn't depend on the size of the graph or the size of the image, you have this efficient parameter sharing property. On the other hand, you have transformers, which have the familiar attention mechanism. Here you have sequences, and typically you want to do some kind of next token prediction. So you can think of the graph as kind of a line graph where you still connect things that are at high distance. Okay, so just keep those examples in mind and I'll return to them later. But I want to sort of give you some overview of the early methods in graph learning that were more common about a decade ago, just to give you some historical context. So the early methods, generally people looked at node embeddings or graph embeddings, which are really graph kernels, they call them. So the idea of a node embedding is to map nodes into some low dimensional embedding space. And you want the property that similar nodes have similar embeddings, right? So there were these works like DeepWalk and Node2Vec, which essentially produced node embeddings. And graph kernels are similar, except you embed on the graph level. And the idea is that you have some machine learning task. You can basically pre-process the graph, produce these node embeddings, and use them for various downstream tasks. Okay. So now how do we think about similarity of node embeddings, right? So, you can think of similarity of two nodes given by their embeddings in terms of an inner product, which tells you how well they're aligned. Okay, so you want node embeddings to maximize this inner product for edges UV that are similar, or nodes UV that are similar. And how do you decide if these are similar? So if you have a supervised learning task, you can learn these node embeddings based on the labels for the tasks, right? If certain nodes have the same labels. The other approach is unsupervised, where you don't have a specific task, but you learn node embeddings according to some structural properties of the graph. Okay. So one of the key insights in these works that I mentioned was to look at random walks. So you think of two nodes as similar if they occur commonly together in random walks. And the idea is that random walks capture some local information as well as some, longer range multi-hop information. So the basic idea is that you sample some random walks starting at different nodes, and you collect random walk statistics and, figure out which nodes tend to appear on random walks starting from different nodes. And then you optimize these embeddings by defining some kind of loss function that you can use SGD on. Okay, that's kind of the basic overview. And both of these works, DeepWalk and Node2Vec, essentially do this. The only difference is in how they sample the random walks, right? So DeepWalk uses fixed length, unbiased random walks. Node2Vec uses biased random walks that allow you to kind of interpolate between locally exploring the graph versus kind of going longer range. Okay, and just to give you an example, there's this famous kind of learning task that people looked at called the karate graph. It's a simple graph, simple node classification problem. The classes are given by these colors indicated there. And you don't have any features or anything fancy. You just look at the topological structure of the graph. And using something like DeepWalk, you're actually able to recover these clusters. So you can look at the figure on the right, which has some two-dimensional node representations. And you see there's this clustering. Okay, so node embeddings, I think, work fine in a number of instances, but what are their limitations? So one of the biggest limitations is that you can't really get embeddings for nodes that you haven't seen during training, like generalizing to new or dynamic graphs. Okay, and it's also unclear how you incorporate features because nowadays you typically have a lot richer data that you're given with your particular task. Okay, and the solution that has kind of emerged in the last few years is the so-called graph neural network, which is a means of deep representation learning for graph data. Okay, so let's go back to this convolutional network intuition that I told you to hold on to, right? So the idea is you have some kind of filter that lets you aggregate information from a neighborhood, and this is done using weight sharing in this parameter efficient way. That is, the filter size does not depend on the overall graph size. Okay, so GNNs essentially generalize this intuition to general graphs. But of course, the challenge here is that in a general graph, neighborhoods tend to look different. So in a grid graph, pretty much, the neighborhood of every node looks the same, right? Because it's a grid. The only exception is sort of on the border, but you can kind of zero out things that go outside, right? But in an arbitrary graph, the neighborhoods can look quite different. Okay, so let's get into what is a graph neural network. So generally, they occur in this framework called a message passing network. So the idea is that each node sends a message to its neighboring nodes that combines node, edge, and graph level features. And you do this iterative message passing procedure. Okay, so I'll describe it in a bit more detail here on this next slide. So you start with these initial node features, h sub u, indexed by 0. And the first step is you compute this message given by m sub uv, that's in blue, right, which combines the node representations from the previous time step along with any edge features. And then you perform this aggregation where for each node, you take the messages from every neighbor, okay? So you look at that multi-set, and then you apply this function f aggregate. Now, one of the keys here is that you want this f aggregate to kind of generalize to a variable number of arguments, and you want it to be permutation invariant. So, you know, it should not, the behavior of this network should not depend on sort of how you order the nodes in your graph. Okay, so typically you use something like sum or max or average. You can use things like deep sets as well. And then the final step is to apply this update function where you take this aggregated vector and combine it with your own features. And then this updates the node representation to the t plus first step. Okay, so you basically produce a series of node embeddings that get refined as you do more message passing steps. Okay, and depending on what your ultimate task is, there might be a final readout layer. So if you have like a graph level task, you might want to combine the node embeddings of all the nodes in the graph. Or for an edge level task, say the edge of interest is u comma v, you would look at the node representations of u and v and apply some function to them. Okay, so let's take a look at an example here, right? So we have a particular graph, and you know, I've used colors to depict the node representations or the initial node features. So we start with this graph in the top left corner where pretty much all the nodes have the same features except that orange node on the top. And what we do is first do this aggregation step. So for each node, we take a look at the multi-set of its neighbors, right? So that's indicated in the smaller text to the side of each node. This is in the top right corner. Okay, and then now we produce some new set of features coming from this aggregation. And then we combine the top two graphs to get the bottom left, right? So for instance, if we look at this, the bottommost node, it's a blue on the left and the orange on the right. So you apply some function that takes blue and orange and outputs green. Okay, and then you have like some readout layer, which, you know, converts these to final positive or negative predictions. And, you know, you can similarly keep doing this, right? So the image on the left is what I just showed you, but you can continue doing more rounds of message passing. Okay, so this is kind of the general idea. Okay, so now let's take a look at a couple of common, popular kind of early graph neural network architectures. So one of the simplest ones is the graph convolutional network, or GCN. And most simply, I think you can understand it by this update rule at the bottom, where you stack your node representations into, you basically column stack them into this matrix big H, right? So each column, so this thing has n columns, and each column is the representation of the node after the teeth message passing step. And you right multiply it by this normalized adjacency matrix. And then on the left, you have this learnable weight matrix, okay? And then you kind of take this matrix product and you apply this nonlinear activation function. Okay, and the idea, again, one of the keys is that this W matrix is has a size that is independent of the number of nodes in your network. Okay, so this kind of gives you efficient parameter sharing. Okay, so you can also cast this into this language that I showed in this earlier slide, where your message is basically you take the node representation from the previous step, you normalize it by some, degrees, and then you do a sum aggregation and apply an update function. Okay, so the top there is basically equivalent to this update rule. Then there is another popular architecture that, again, was about 7 years ago, which is GraphSage. So again, it follows this similar message passing approach, but one of the key insights they had was to do some kind of sampling. So in their message passing, they actually look at 2-hop neighborhoods, not just immediate neighbors. But since this blows up, they actually do some kind of sampling. And that can be shown to give some improvement in certain cases. Again, we can kind of describe it in this GNN language with this aggregation function and update. The message is pretty simple. You just pass the previous node representation, and then the aggregation is basically some kind of average over some sampled neighbors. Okay, we turn to a third, the final example, which is what's known as GATT, or Graph Attention Networks. So this one has an interesting idea, which is that when you do the message aggregation, instead of kind of uniformly aggregating the messages, you want to assign importances to various neighbors. And how can you do this? Well, the idea is to use some kind of attention mechanism to get scores for various neighbors. So maybe certain neighbors are more important than others, and you can use attention to kind of learn this. Okay, so it's going to look something like this. The key step is basically this middle aggregation step, where we have these alpha sub UVs, which are coming from some leaky ReLU based attention. Don't need to focus too much on that attention computation there, but basically it's some kind of softmax thing applied to an attention mechanism. Okay, so hopefully I've given you some basic examples of graph neural networks here. Now I'm going to turn it to Adrián, who's going to tell you a bit about various tools that come up in graph learning.
I'm going to do it from here. Okay, can you hear me? Yeah. Hello, everyone. Now I'm going to talk about some concepts and metrics that we use in graph theory that are going to appear in the rest of the slides, both for the expressivity part and both for the challenges of GNNs and the over problems. Those concepts that I'm going to explain now, they are related with the spectral graph theory, that the spectral graph theory is the study of the eigenvalues and eigenvectors of the graph Laplacian. So, yeah. A bit more technical, the graph Laplacian is basically the degree matrix. The degree is the number of neighbors that a node has. And the degree matrix is a diagonal matrix, and it's pointed the diagonal. There is the degree of that node. We also have the normalized version by the degree, which is called the normalist Laplacian, which is the calligraphical. So we have studied the decomposition of eigenvectors and eigenvalues in this matrix. So the idea here, and I think the most important thing for graphs is like thinking of the eigenvectors as a set of orthonormal functions that minimize the variability of the node signal with respect to the graph structure. What I mean by that? The variability of a node signal is if we define a signal over the nodes in the graph, let's say one scalar number for each node. The variability is the first function. I think the pointer we cannot see very well, but is the first function in the green box, which measures the difference of this signal between the neighbors in the graph. It happens that as the Laplacian matrix here is positive semi-definite, then this difference between this variability of the signal, it's the loss of a problem, but if you solve it, you have the eigenvectors. So the eigenvectors, actually you can find it in a graph, minimizing the variability of the node the variability of the signal of the nodes in a graph structure. And how does it work? So first, the first eigenvector and the first eigenvalue. The first eigenvector is a constant vector because you minimize the variability. Every node has the same value. And then the variability is 0, so the first eigenvalue is 0. And then the next eigenvectors and eigenvalues are orthogonal to the previous one. So the second eigenvector will be the solution to this problem, but being orthogonal to the first eigenvector. And then the eigenvalue is just like the energy of this signal. So we can see them as a set of orthonormal functions and that minimize the variability. And I think this is very important here. As an example, we can see here the first, second, fourth, and high eigenvectors plotted over the graph. So the first is constant. The second one is smooth over the graph because it has to be orthogonal just to the first eigenvector, and so on and so forth. So the first eigenvectors gave us a very global set of coordinates, and the higher eigenvectors give us some more sharp coordinates on the graph. So these eigenvectors are going to be used later in the talk. Another important concept is the Cheeger constant. The Cheeger constant is it's also kind of known as the mean cut problem. So it's literally which is the minimum number of edges that you have to remove in a graph to disconnect the graph in two parts. So here, partial S, the numerator, is the number of edges that go from a community to a community. And the Cheeger constant is the subsets of nodes that minimizes this value. So like the bottleneck in the graph. The problem is that this problem is NP-hard, but there's a Cheeger inequality which tells us that this bottleneck in the graph is bounded by the second eigenvector of the eigenvalue of the Laplacian. Why is that? Without going into much detail, is because actually this mean cut problem, you can formalize it as using the Laplacian quadratic form, which is there in the bottom left. That if you realize is the numerator in this Rayleigh coefficient, that if you minimize it, you have the second eigenvalue. So long story short, the most important thing is that Cheeger constant, the size of the bottleneck in the graph, is bounded by the spectral gap. The spectral gap is the second eigenvalue of the Laplacian. And here we have an example, two communities. If we keep adding edges between the two communities, then the spectral gap just increases. And last but not least, we talk about effective resistance and commute time. The effective resistance, or the commute time, the commute time is a pairwise metric between nodes, which is the expected number of steps of a random worker to go from one node to the other and came back. Given, as Ameya explained it before, given as it's based in the random walk, it captures the global behavior and the long-range dependencies. The heating time is just the expected number of steps from going to one node to the other. That's why the H there, and it's come back, it's symmetric. And just the effective resistance is the commute time divided by the sum of decrease of the nodes in the graph, which is the volume of J. So we can see in the picture that the more and the shortest paths between a pair of nodes, the smaller this distance is, the smaller the effective resistance is. And here in the bottom graph, if we add just one edge, all the effective resistance changes, even if the shortest path doesn't change, because it captures all the global structure. So yeah, it can be computed just for completeness in a spectral manner, either with this formula first or just based on the pseudo-inverse of the Laplacian. So, but just the intuition is that it's a spectral metric. And as the eigenvectors were capturing all the global coordinates, it also does this metric. And just as an example, yeah, it's called effective resistance because If you are more aware of electrical circuits, you can think of as the edges as resistors, and then you measure the voltage between two nodes. That's what we call effective resistance. That is very well used in theoretical computer science by Lovas, Daniel Spielman. So it has a lot of theory behind that will allow us to draw conclusions about GNNs. And just an example of what do I mean by expected number of steps of a random walker. Imagine that we want to measure the commute times or the proportional effective resistance between U and V. So this is the heating time between, this is one path that we can take between U and V, and this is one other path that we can take. So there are 6 steps, but there are also another paths in the graph, so it's 5 steps. So if we do this in all the paths in the graph and we do the expectation, that's a commute time, and that's why it takes in, it captures the global behavior. So now I'm going to head out to Ameya, now that we have these concepts, to start to talking about transformers, expressivity, generalizability, and the challenges of GNNs.
All right, thanks, Adrián. So yeah, I'll continue onwards. So if you remember, we talked about graph neural nets, which operate via message passing. The other kind of aspect I told you to keep in mind for some intuitive purposes is the transformer architecture. So again, transformers have arisen in mainly a sequence context. But now we have transformers that operate on graph data. So I'll describe some of this. And, there will be some techniques that come up over the talk that I think, Adrián referred to some of the tools that we'll be seeing. Okay, so again, this is just a reminder kind of the standard transformer, the vanilla transformer in Vaswani et al. And, again, this is kind of in the setting where you have a sequence of tokens and you want to do next token prediction based on a past context window. So again, here you typically have, you can think of it as a line graph. So what are graph transformers? Well, basically it's an extension of transformers to data that appears on an arbitrary graph. So instead of doing next token prediction, we want to actually learn node representations for the various nodes in the graph. So one of the key ideas here, which differentiates the graph transformers from the message passing GNNs, is that you typically have a computation graph that is different from the input graph structure, right? So in the GNN world, you did message passing precisely along the edges of the input graph of your data set. But here, you typically have a computational graph that is divorced from that. Often, the most common case is where you actually connect all pairs of nodes. Okay, so this, brings some advantages, but also brings challenges, right? So how do you account for this loss of inductive bias from the input graph structure if you're just kind of throwing out the input graph? And, how do you identify nodes within the graph, right? So in your typical sequence transformer, you have a natural ordering and, use some kind of positional encoding, right? So there's a natural kind of extension of that to the graph world. And then there's also scaling questions coming from the number of connections. Okay, so one of the early kind of graph transformer architectures was proposed by Dwivedi and Bronstein about 3-4 years ago. And it's pretty much familiar architecture here. You have this QKV attention. The main difference is that what you're feeding in and pulling out of the graph or pulling out of this network is this node emitting H. Okay, and there are a number of newer architectures that are, more or less based on this general principle. So we'll talk about a few of these. And, I alluded to this earlier, but basically, in the natural kind of sequence transformer, you use positional encodings, and these allow you to distinguish different tokens in the sequence, where you are. You need a similar thing for graphs, but it's a little bit more challenging. So in sequence transformers, you use these sinusoidal functions, sine and cosines. One way to look at sines and cosines is they actually arise as eigenfunctions of Laplacians, which Adrián was discussing a few minutes ago. Laplacians for Euclidean graphs, essentially. On graphs, we can kind of generalize this notion where we look at the graph Laplacian. So this is a well-studied quantity in spectral graph theory. And it turns out you can derive positional encodings by taking some number of the top eigenvectors and using these as positional encodings. One can also use learned positional encodings, which operate on top of these Laplacian-based features, right? So you have some trainable weights. And this is essentially the idea that was used in this work SAN, or spectral attention networks, from a few years ago. And not too surprisingly, the positional encodings actually can make a big difference. So if you look at this zinc data set, you look at the last row versus the second last row, you get quite a big difference. And it's not surprising because without the positional encodings, you can't really know where the node lies within the topological structure. Another common graph transformer architecture is the so-called graphformer. Again, they use kind of a similar attention mechanism, but they have these two key new ideas. One is to use what they call centrality encoding. So for each node, they use some learned vector based on the in degrees and out degrees. And then more interestingly, they also use an attention bias that's based on shortest path distance. So this is some kind of encoding where you have a node Vi that attends to Vj. You do the regular attention computation, but there's this bias term that's based on the distance between Vi and Vj. Okay, so again, the left side is pretty much your standard QKV attention, and you have the centrality and spatial encodings coming into the model. And it turns out that their approach works pretty well in molecular graphs. In fact, there's this large-scale molecular data set on which they were able to move the state of the art, and they got pretty good performance on other molecular and chemistry data sets. Okay, so the final thing I want to discuss pertaining to graph transformers is this scaling issue. So, the typical transformer, kind of vanilla transformer, whether in the sequence world or in the graph world, you have a quadratic dependence that's coming from kind of connecting every node to every other node. Okay, so in the sequence world, there was this plethora of works that tried to construct sparse attention mechanisms where instead of using the complete graph, you would sparsify this into some smaller number of edges, right? But again, these are mainly for sequence-based transformers. Turns out you can do a variety of techniques for graphs as well, and these have popped up over the last 2 years, basically. So Xformer, NodeFormer, GoFormer, pretty much combine whatever you want with former, and probably there's some paper with that name. Anyway, I won't discuss all of these, but just to give you a sense of some ideas, right? I'll talk about Xformer, which is one of our works from ICML last year. So here we actually combine kind of 3 types of edges for the computational graph. So one of the key ideas is to use what's called an expander graph. So This is commonly used in spectral graph theory and mathematics. So they're basically sparse graphs that have good global connectivity. So it's kind of like a spectral approximation to the complete graph, but it only has a linear number of edges. And what we do is combine this with the original graph as well. We use edges from the original graph to preserve some of the inductive bias. And then we also have these global sync nodes or virtual nodes that connect everything, that connect to every node in your original graph. Okay, and then this computational graph is basically formed by taking all three types of edges. Okay, so you get kind of good properties here, but you don't need n-squared edges. Okay, and this can be viewed as a sort of analog of Big Bird, if you're familiar with that, in sequence transformers. Okay, and it turns out this was actually able to move the state of the art on a number of different graph data sets and tasks. Notably, you get this long-range performance. So there's this benchmark called the long-range benchmark of tasks that presumably require you to learn long-range dependencies. So obviously, if you have a dense computation graph where you're connecting every node to every other node and kind of throwing out the input graph, you can sort of communicate directly. But the question is, when you sparsify the graph, are you still enabling those long-range dependencies? And at least the answer seems to be yes, based on the improvements. Okay, so just to kind of recap, we described graph neural nets based on message passing. And then on the other hand, we described graph transformers. They have their various pros and cons. With message passing, you directly capture the inductive bias from the input graph topology. The computation is efficient because you're not constructing any dense computation graph. But there is some difficulty with long-range dependencies because essentially, if you have a large diameter in the graph, you need to do message passing for at least that many rounds just to have those nodes communicate, right? And as many of you probably know, when you have too many layers, you can have issues such as vanishing gradient and things like that. So there are some issues with message passing. Graph transformers, on the other hand, don't suffer from these issues. But there are some questions about how do you overcome the loss of the inductive bias, given that you're kind of throwing it out for the computation. So again, this can be rectified using positional encodings. Yeah, and then obviously the computation, how to decrease the quadratic dependence, right? These are all challenges. And I should note that there are approaches that actually combine both message passing and graph transformers. So there's this amazing work called Graph GPS from a couple of years ago that kind of alternatingly performs message passing and attention. And they were actually able to get state-of-the-art performance on a number of benchmarks. Okay, so now I'm going to move into the next part of the tutorial. So we'll talk about questions of expressivity. So here what we're concerned with is determining what kind of functions a message passing GNN can actually represent, right? What sort of functions can we even capture using these model architectures? So typically what the lens through which this is analyzed is through something called the Weiss-Feiler-Lehmann isomorphism test. So just to give you some history, this is actually an algorithm that tries to determine whether two graphs are isomorphic. And in the 1960s, it was actually introduced as a candidate algorithm. we now know that graph isomorphism is a pretty hard problem. So this doesn't quite work. It's more of a heuristic, but there are certain pairs of non-isomorphic graphs that this test cannot distinguish. And it turns out that GNNs are known, at least vanilla GNNs are known to be bounded in expressivity by the Weiss-Furler-Lehmann test. So that is, if you do some kind of graph classification problem, you cannot hope to distinguish graphs that cannot be distinguished by the WL test. So what is this WL test? So essentially what it does is it performs some kind of hashing at each step, where for each node you look at the neighbors and you do some color refinement. So I'll describe this on the next slide. Okay, so let's say we are given a graph. Okay, this example has 5 nodes. We start with some coloring of the graph. Typically, we assign the same color to all the nodes. And then at each step, what we do is we look at the set of neighbors of each node, that is the multiset, and we hash the multiset to a new color. Okay, so if we look at this first step, what happens is all the multisets have only blue nodes, but there are 2 nodes that actually have 3 neighborhoods. That is, they have a neighbor multiset of size 3, and the remaining nodes have multisets of size 2. Okay, so that allows you to distinguish these red nodes from the green nodes, and then if you do one more step, you get further refinement. Okay, so you can do this procedure, and it's known that it eventually converges after some reasonable number of steps, basically n steps. And what you can do now, if you have 2 graphs and you want to determine if they're isomorphic, you pretty much perform this procedure in parallel on both the graphs. And you know that if at some stage the set of colors on one graph is different from the set of colors on the other graph, you know for a fact they're not isomorphic. And if you do not ever detect non-isomorphism, then you pretty much call them isomorphic, right? So it's not too hard to see that if it's determined to be non-isomorphic, it actually is non-isomorphic, but there can be false positives. Okay, so this is pretty much the algorithm that I described, just written out more formally. Okay, so as I mentioned, the 1WL test does have some failure cases. So this is one example on the right where these 2 graphs are clearly non-isomorphic because the bottom one has a cut edge whose removal disconnects the graph. But if you do the 1WL test, you will not be able to distinguish these. Okay, and here there are some more examples of pairs of graphs that fool the isomorphic, that fool the 1WL test. In particular, I should note on the left side, you actually have pairs of D-regular graphs. So usually, if you have non-isomorphic, pairs of D-regular graphs, those cannot be distinguished. It's a fun exercise to think about why this is the case. There is a sort of extension of this first order WL called the K order, where you pretty much do the same thing, except instead of assigning colors to individual nodes, you assign colors to K tuples of nodes. Okay, so you pretty much do the same thing, except that you have some notion of neighbors of K tuples, and you again do color refinement. And usually as K increases, you get more expressive power. So generally in the GNN world, we like to look at expressivity in terms of this WL hierarchy. There are some works that propose to look at things beyond this usual hierarchy. There's this interesting paper from last year, which actually proposes looking at biconnectivity metrics. So they argue that looking at WL is limiting in some ways, and they propose sort of a new framework. Okay, so having discussed the limitations of graph neural networks, one natural question is, can we get beyond these limitations? So a lot of the research in graph neural nets over the last few years has sought to improve the expressivity of GNNs going beyond these limitations. And I like to think of kind of three broad buckets or three types of approaches to improving expressivity. The first one is to add features, again, that capture some kind of structural properties. The second approach is to modulate the message passing mechanism itself. And the third approach is to kind of alter the underlying graph. Okay, so let's take a look at the first one. So the idea here is that you want to add some additional node, edge, or graph features that capture some kind of structural or positional information or something about your domain. And you can kind of directly incorporate it into the message passing scheme. So usually you compute these features offline before you train. Okay, so one simple example actually here is that, even if you kind of pick random features for every node, that already enables you to go beyond 1WL. This was shown in a work of Sato et al. And a subsequent work. There are more sophisticated approaches. One well-known one is graph substructure networks, or GSN. So the idea here is you decide on some set of subgraphs or some kind of substructures, and you want to count the appearance of each node or each edge within orbits of these substructures. Okay, and then you kind of use these features in your message passing. Now, one question you might ask is, how do you choose these substructures, right? I can pretty much choose any sort of subgraph. So usually this is domain specific, right? You have some kind of knowledge about your domain that guides your choice. So for instance, in the case of molecules, people generally know that cycles are very important. Things like 3 cycles, 6 cycles, chains as well, chains of molecules. So you can use those kind of structures. Okay. On the other hand, there might be cases where you don't have a ton of domain-specific knowledge and you want some kind of general structural information about the graph. So this is one of the things that was addressed by this work on affinity measures from NeurIPS last year. So what this work does is uses a variety of measures such as effective resistance, hitting times, and what we call resistive embeddings. And these are kind of general topological structures. So I think Adrián again talked about effective resistances and hitting times. So again, just to remind you, one way of looking at it is you have a resistive network of resistors in an electrical circuit, and you want to measure what is the effective resistance between 2 nodes that is given by Ohm's law. Okay, so this actually just encoding effective resistance features for edges already enables you to distinguish different classes of nodes that you would not be otherwise able to distinguish. Okay, so effective resistance, hitting time, these are scalar values. We also have something called resistive embeddings. These are vector valued features, and they actually satisfy this interesting property that the L2 square distance between the embeddings of two nodes is equal to this effective resistance. So in some sense, they're richer than just the scalar values. Okay, and as I mentioned, you can incorporate these into the edge or node features. And one interesting result is that using this kind of approach, we were able to actually improve the state of the art on this large-scale molecular data set. And it's kind of interesting because a lot of the other approaches that were tried before, they made use of very domain-specific information. So things like molecular coordinates and very molecule-specific features. On the other hand, just using these general kind of topological features that are non-domain specific, one can already beat some of these other approaches. Okay, so that is that's the first approach to improving expressivity. The second approach is to modulate the message passing mechanism. Okay, so what do I mean by this? Well, we already saw one example of this. So this was graph attention networks, or GATT, where we allowed some non-uniform or anisotropic aggregation of messages by kind of weighting the neighbors differently. There are some other works like identity-aware graph networks, which in a nutshell, what they do is for each node whose embedding you want to compute, you kind of unroll this message passing computational tree, and you use a different message passing rule for the node itself versus all the other nodes. There's also directional graph networks. Again, they do some anisotropic message passing, but they use Laplacian flows to guide the direction of the message passing. Okay, and then the final approach is to modify the underlying graph, okay? So use a computation graph that is different from the input graph. So, we talked about graph transformers. You can view graph transformers as some example of this approach. So again, the idea is that you don't want to necessarily be restricted to the input graph, especially when you have a data set where the graph can be noisy. So one such approach, besides graph transformers, is use of these higher order GNNs. So I described this series of WL tests, the K order WL test, which operates on tuples of K nodes. So basically you can design a GNN that does message passing on K tuples of nodes. Okay, and it turns out these higher order GNNs, can give you more expressive power, and there's this nice hierarchical summary in the work of Morris et al. One thing to note, again, you do get this n to the k dependence. So typically, if you have large graphs, you can't really go for k bigger than 3, for instance. Okay, so next thing I will talk about is generalizability. Okay, so we spent the last few minutes talking about expressivity, that is, what kind of functions can be expressed or learned by a network, theoretically. But even if you enhance expressivity, does this necessarily translate into better, say, test performance in practice? One plausible answer to this is no, because it's possible that you have a more expressive network, but you actually lead to more overfitting. Somewhat surprisingly, in practice, we don't observe this to be the case, and there are a lot of instances where more expressive networks actually result in better generalization. So if we look at these graph substructure networks that I was describing a few minutes ago, we've often observed that test MAE or test performance on a number of data sets is actually better despite the improved expressivity. So one way of kind of understanding this, a tool from statistical learning theory is the so-called VC dimension, right? So in that setting, like consider you have a set of functions that do binary classification. You say that a model F shatters a set of data points if for any assignment of labels there's some model in your model class that correctly classifies all the points. And the VC dimension is simply the largest number of points that are shattered by F. So from statistical learning theory, we know that VC dimension gives a bound on test error in terms of training error. Okay, so if you look at this inequality at the bottom, E out is your test error, En is your training error. So you can bound your test error in terms of the training error plus this additive quantity. And the main thing here is that if you get a smaller VC dimension D, then you get a smaller additive term, which more tightly bounds the test error. Okay, so there's this nice work from ICML last year, which tries to understand VC dimension of graph neural networks in the binary graph classification setting. And I won't go into the details, but they basically determine a variety of settings under which you can actually tightly characterize the VC dimension. Okay, so this gives some insight into generalization capabilities. One question that you might ask is, or one question that still remains somewhat unanswered from this work is, why do you get increased expressivity leading to better generalization even when you keep the training set more or less the same, right? Because if you look at this this additive quantity here, there's this dependence on M, which is your training set. So you can kind of increase the VC dimension, but if you sort of correspondingly increase the training set, you can keep this quantity constant. So generally, if you increase the expressivity, you're going to get like a higher D value, right? Which will lead to a looser additive constant here. But what we observe in practice often is that even if we keep the training set the same, we still get better generalization as expressivity increases. So there's actually this work that looks at this problem, and we have a poster on this on Thursday, so shameless plug. Just to give you a preview, we again consider linear classifiers, and we look at generalization error, characterization of it based on margin in linear classifiers. Okay, and there's a lot of interesting theory in the work. There's this nice paper of theory of pack learning and partial concepts from Fox, and we essentially extend this to MPNNs. This gets margin-based VC bounds. And furthermore, you can also get this nice property that, MPNNs in this linear classification setting, they exhibit some kind of convergence to this max margin solution. So this is under gradient flow or gradient design. Okay, so again, it's a preview of Thursday. Come to the poster. Okay, so at this point, I'll hand it to Adrián again, and he will tell you about challenges of GNNs and some of the more modern directions.
Cool. So yeah, after looking at the expressivity and generalizability, we're going to talk a bit about some challenges and some problems that we find in GNNs due to the problems when you do diffusion on graphs. So the problems are called underreaching, oversmoothing, and oversquashing, just to give you a brief introduction. First, I would like to explain like a common origin of the problems. GNNs, as we have been commented, arise just to leverage information in the structure of the graph. The idea of the GNNs is that you develop a methodology to take advantage of the information that there is in the structure of the graph, in the manifold. In the first words, they assume locality. When you do inference, you assume some kind of localities, and as in semi-supervised learning, if you are close on the manifold, then the probability of X is kind of similar. So you assume some kind of a smoothness locality when you do inference. The problem, as Ameya also has mentioned, is that there's a lot of tasks that are long-range tasks. That means that the structure itself is important, but the important information depends is on different parts of the network. They should communicate, but they don't. So actually, once you have these problems, we can talk about them in terms of the diffusion. So we are going to talk in the next minutes about the diffusion on graphs. First of all, which is long range, more in detail, basically are tasks that depend on long range interaction between nodes in protein-protein interaction or in different tasks. Maybe are different nodes that are farther away, but that they should communicate in order to inform better the task. And also homophily, heterophily. How do we define these concepts? A homophilic graph, in terms of when you are doing prediction of nodes and the nodes have a label. The idea if a graph is homophilic, it means that the nodes that they have the same label are connected with each other, and there's a continuous space of the metric until the other way that it's called heterophily, which is that most likely that you connect with nodes that are not from your label. There are a lot of metrics. Sometimes we measure even long range with homophily metrics. We will talk about that this can cause some problems later. But these are the classical problems, heterophilic problems and long range problems when we cannot rely on the locality smoothness assumption. So this causes some problems. These are the problems: underreaching, oversmoothing, and oversquashing. And the benefit of time, I will talk about them in detail. So first, I will talk about underreaching. Basically, is the inability of the nodes to be aware of the information of nodes that are farther away than the layers that you put in the GNN. Basically, it means that if you do K layers in a GNN, so K message passing interactions, those nodes that are farther away than K layers, you are not going to access to that information. That's why the problems on long range and heterophilic tasks, it's important, because there are nodes that are farther away that should interact. So in this problem, you can think, okay, we increase the number of layers of a GNN, and yet it's valid, and then the nodes will communicate with each other. But as we will see in the next problem, it's not as easy as that. Next problem is called oversmoothing, or OSM as abbreviation. This problem we said before, okay, we put a lot of layers and then nodes communicate. It's not easy because it's known that when you stack many layers on a GNN, as k tends to infinite, then all the features of the nodes converge to the same point. Let's say that if there is one dissimilarity metric, it converges to 0 as we increase the number of layers. Basically, it's the tendency of the nodes, of the node features to approach the same value. So if all the nodes end up having the same value, then it's not useful for our task. Conceptually, this is cause, or the reasons that we are going to be looking at is that how many times do we mix? So the more layers, the more mixing. And also the structure of the graph and the GNN architecture, they are actors that play a role into how the features mix each other. So they will also have a role. This problem, it's independent of the problem radius, and I say independent because no matter what are the initial features, that if you stake k number of layers, they will converge to this oversmoothing problem and they will converge to the same value. I say independent because if you don't have a long range interaction, maybe you don't have to stack that many layers, and then this won't happen. But theoretically, it will happen. So, yeah, and of course it decreases accuracy if all the features collapse to the same nodes. Here's a bit of a spoiler because this is accuracy and the number of layers of a GNN, so it decreases, but there will be some approaches that kind of mitigate this approach. Yeah, and how do we measure over squashing? There are a lot of metrics, but there are some consensus on using the Dirichlet energy. The Dirichlet energy is literally as we said before, as we saw before, the numerator of the Rayleigh coefficient, the variability between the nodes in the graph. So if we have a signal, we measure like the difference between me and my neighbors, and we sum up over all the nodes in the graph. So the more similar the nodes are with it, the feature of the nodes are with each other, the lower the Dirichlet energy. And this is what we can be in this synthetic example. Just a recap. The eigenvectors, if you remind before, there were a set of orthonormal functions that minimize the Rayleigh coefficient. And the Rayleigh coefficient, the top part, is nothing else the Dirichlet energy. So we can think about the eigenvectors as functions that minimize the normalized Dirichlet energy on the graph. So it's very closely connected also with this approach. Okay, now we know what is Dirichlet energy. So the more similar are the features, the lower the Dirichlet energy. And we see here a couple of experiments, one by the survey by Rashidal, that the GNNs, as the number of layers of increases, the Dirichlet energy decreases. And not only that, but in this example here that I made with Rishabhanan, the denser the graph is, so the denser is yellow, and the more sparse is purple. The denser there is, the faster is the convergence. And why this happened? So we can look this problem from the stationary distribution perspective in terms of how we do a diffusion in the graph and what happens with a signal in the graph. Okay, so imagine that we do a diffusion with the random walk matrix. The random walk matrix is just the adjacency matrix divided row-wise by the degree of the node. And we have a signal that it's called F. It's a distribution over the node, so the here sums to 1. And if we want to see how is the distribution after key steps, we have F transpose times P up to K. And this will give us the distribution over the nodes after K steps. And it's known by the stationary distribution and the study of this distribution that no matter what is the input signal, that's very important, no matter the feature of your nodes, this distribution in the limit asymptotically will converge to the stationary distribution. And the stationary distribution is like the distribution of the degree, the degree distribution. So no matter what my feature is, that in the limit, I will converge to my degree divided by the sum of all the degrees in the graph. And here we have two examples that in the graph in the middle, the blue is the initial distribution. As you see, are very different, and they converge to the same one, which is the green distribution. And which is the rate of convergence, so how fast this behavior happens, which it's important. We want to avoid this behavior, so we want to see how fast it happens. Basically, long story short, the difference between the distribution over k steps and the stationary distribution is bounded by the eigenvalue here, and a constant of the log at the degrees, the inverse of the eigenvalue. So the highest is the second eigenvalue, the highest is the Checker constants. Like the more connectivity in the graph, the easier it is to the features to mix with each other. We also can see it from a connection with the effective resistance. And rather than doing the diffusion with the Laplacian, the random walk matrix, we do the diffusion with the heat kernel, which is this formula here, the exponent of minus TL of the original signal. So when we do this a lot of times, so here T is the time, can be seen as the number of layers, it converges to the average of the signal. No matter what the input signal is, the signal will converge to the average rather than to the stationary. So we see here two examples of two types of diffusion of graphs that will lead us asymptotically to have the same features if we put a lot of nodes. The rate of convergence here, the eigenvalues determine the rate of the convergence, so the speed of the convergence of this signal to the average signal. And the connection with effective resistance is that there's time constants that will tell us how fast you converge to the average distribution. And we know that the total effective resistance, which is nothing else than the sum of all pairwise effective resistance is the nodes, it's also the sum of the inverse of the eigenvectors, which is the sum of time constants. So the higher the effective resistance is in the graph, so the worse the connectivity because nodes are more spread out, then the time constants would be higher. Then this means that the mixing will be lower. So yeah, that happens. Yeah, we have seen this, but you will be wondering, but GNNs are much more than that. You have a lot of different actors in GNNs, like feature transformation, nonlinear feature transformation, nonlinearities, feature matrix, etc. So there is some work. I won't go into detail for the benefit of time, but the idea is that they study this effect with GNNs, and they study the effect of the structure, that they lead to a conclusion similar as the one before, that is related with the eigenvector. They see the effect of the weight matrix, so the feature transformation matrix of the GNNs, and also the activation function. A long story short is that the Dirichlet energy from, if you stack too many layers in a graph, and we are talking that the Dirichlet energy goes down. They see the effect of how that each component affect the Dirichlet energy from one layer to the other. So the Dirichlet energy from the next layer, it's upper bounded upper bounded by the Dirichlet energy of the previous layer by a constant that depends on the structure here in lambda 2, and also by a factor that depends on the singular value of the feature matrix. So the higher the norm of the feature matrix, of the weight matrix, the higher the norm of that matrix, the higher is going to be the over squashing between one layer and each other. Because you can think about the West matrix as if it encodes the interaction between the connected nodes, if it gives a strength to that connection. I also want to mention that then, in practice, not always correlates over smoothing with over squashing with accuracy, and sometimes it's very fragile because in GNNs we have a lot of factors that we can put. We can modify the aggregation function. We can modify all the dynamics on how do we aggregate nodes. We can add normalization. So just changing the aggregation function. Here, if you look at the middle, the y-axis is the training epochs and the x-axis is the number of layers. So we just focus on the horizontal with the mean aggregation, which is the left part in the screen. The Dirichlet energy on each layer it's reduced, but with the aggregation function, it kind of explodes. And both of them doesn't have a very good accuracy when you stack k many layers. So just speaking more broadly, your GNN will perform or will do over smoothing if it's low frequency dominant. It's basically that the Rayleigh coefficient will tend to 0 when when you stack a lot many layers. And this bound here gave us more or less when it happens. And if your GNN, no matter the components, doesn't perform over smoothing, it's called high frequency dominant because actually prioritizes the frequency of the high eigenvectors that, as we saw before, are the ones that are more sharp over the structure. Yeah, basically for the solutions, I'm just gonna mention some of them. Yeah, I think we're a bit ahead of time, so I'm just gonna go over them. We can do normalization of the node embedding. So if I normalize the nodes at every layer, then the Dirichlet energy doesn't collapse. I can sparsify the graph as well. You can do regularization of the weight matrix, add a skip connection, and change the GNN dynamics like straight away. So there are a lot of approaches. So we can just do the normalization. After we do the message passing, we normalize the nodes again, so they will never converge to 0. We also can do graph sparsification, and not going in detail into the bounds, but the idea is that if you sparsify the graph, you decrease the spectral gap. And as we showed before, this spectral gap, this second eigenvalue of the Laplacian, is the one governing how it's going to be the mixing of the nodes. So there are different strategies like random sparsification, because no matter how you sparsify, this value could be down, or different strategies that are based on neural sparsification, or learn how you sparsify the graph. There are also approaches that are based on skip connections. They're basically same as in computer vision and same as in temporal series. You just add again the original signal, so you can enforce the signal again. You don't let it to collapse. You can add the previous layer signal, or you can add even the original signal, which is the one on the right. And also one approach, as we show, there is the oversmoothing happens because of the structure. Oversmoothing happens also because of the weight matrix. So there are some approaches that what they do is try to normalize the norm, to reduce the norm of the weighting matrix. What they do here is they sum up in GCN AI. It's called AI because it's initial residual identity mapping. They try to do orthogonal normalization on the weight matrix. So they force the norm of the weight matrix to be small, and then this bound, they improve this bound, and oversmoothing doesn't happen that much. And this is the figure that I showed before. These are, with the two approaches, kind of the accuracy keeps similar if you keep adding nodes. Yeah, and you can just do the skip connection in many different ways. The idea is that you try to avoid this Laplacian smoothing effect of graph neural networks, and you want to perform some kind of tricks that enhance the high frequency dominant, behavior of the MPNN. Then there's advanced GNN architectures as change dynamics. I want to also mention graph sage and GAT, because if you think about them, they do also some kind of sparsification of the graph. They select the nodes, or they give away a different weight to each connection. So even these architectures that were proposed before, we can explain why they work well based on that. There are physics-informed GNNs that are based on model PDEs and ODEs, and also like recent work about adaptive GNNs that you can learn which messages you actually incorporate for each node, and also the depth of the network, like in a learnable way. So yeah, that's a little recap that I might skip. That the idea is that oversquashing happens when these features collapses. And there are some kind of mitigation strategies, either on the structure or even in the way that we change, or even in the way that we create our GNN. Next, I will talk about oversquashing. That the idea about oversquashing is that as we increase the number of layers, the number of neighbors that we have to aggregate information from increase exponentially. And the problem is that there is, as we increase K, the number of neighbors increases, but this information has to be compressed in the same feature vector for one node. So there's a problem because then the normalized influence that we have is going to be reduced. So yeah, this can be formalized as that the stacking a lot of NPN layers exponentially increases the receptive field of the nodes. And if you imagine a binary graph, a binary tree as a graph, as you increase the depth, then the normalized connection strength between U and V, it's going to be given by this value, which is lower and lower as the depth of the tree increases. This effect is even worse if there are bottlenecks in the graph, so there's only one way for the features of one part of the graph to go to the other, but a lot of information has to be compressed in one single bottleneck in one node to go to the other side. This problem was introduced by Alon and Java and also by the curvature paper of Topin et al. So in the first paper, they say, okay, we'll do a benchmark problem that tries to simulate these things. So the idea is that we have a node that we want to predict for that node, like the one with the question mark, the level of the other node that have the same number of neighbors. So in this case, we will to predict C. The idea is that we can move farther away or we can put closer these two nodes, so the radius of the problem, and to see how GNNs happen. And we see here that as the radius of the problem increases, also the accuracy decreases. So there is some bottleneck in the graph that is not able to distinguish between these two nodes. How we measure over-squashing? As you can imagine, we can measure it with the Checker constants, the effective resistance. There are a lot of ways. We will upload these slides, so you also can have access to them in the web page that we will show later. The long story short is that the Checker constant that we talked about in the beginning, so the size of this bottleneck, we can measure it like that. As it's NP-hard, it's bounded by the spectral gap, by the second eigenvalue. It's also connected these Checker constants with effective resistance. So the maximum effective resistance, it's a bound of the inverse of the Checker constants. It's the same. The more disconnected the graph is, the higher the effective resistance, the lower the Checker constants. And also this is connected with the Checker inequality, just for completeness. And here I would like to stop a bit, even if maybe I skip some methods later, is how do we measure over-squashing in the literature. So the idea is that we have a sensitivity metric, which is literally how much the features of the node U in the layer X0 in this case, affect the features of the layer V, so the source node, on other layer, on a higher layer, rather bigger than the previous one. So it's the probability that two nodes share information with each other. The connection to underreaching is that if two nodes are farther away than k layers, then this Jacobian will be 0. So this is called the Jacobian between two nodes. Then the sensitivity metrics will be 0 because they will never share information. But let's stay with me with this formula because I think it's very, very interesting. So how do we measure if two nodes actually interact with each other? So we compare the self-sensitivity after k layers. Let's say that this metric J give us the sensitivity between nodes V and U and between the layer of the GNN K to M, bigger than K. So let's say between me and other node and the layer 2 and 5, which is the interaction between our two nodes and between these two layers. So the idea is the first term here in the subtraction is a self-sensitivity metric. So it's how much do I affect myself after k layers, minus the pairwise sensitivity that the other node has against me. So the idea is that if I have more sensitivity with myself than with the other node, this would be higher. And we just do this the same, but symmetric. So it has to be symmetric rather than BV and V and then U and V. We have U and U and then U and V. So we call this symmetric Jacobian instruction. It was in Di Giovanni in ICML last year, was proposed by Di Giovanni et al. Basically, it measures the obstruction between two nodes. So the higher is this value, the more obstruction there is, because the more sensitivity I have self-sensitivity I have against to the pairwise sensitivity. And if we want to extend to m layers, we have this metric here, which is just, okay, do it for every layer up to m. And why this is interesting, because it's like, okay, now I have a metric of which is the pairwise sensitivity between nodes, how the features of one node affect the features of the other after m layers, right? So how this metric behaves. So there is also some bounds proposed by Di Giovanni et al. And by Michael Black et al. Last year at ICML. That this sensitivity, first just the normal sensitivity, is upper bounded by the structure of the graph, by the normalized number of paths, as we showed before. But what I find even more interesting is that the Jacobian abstraction, so it's like this sensitivity after m layers, it's upper bounded by a constant with, I advise you to read the paper because it's very interesting. It's also some parameters of the width of the network and the depth, but by some constant and effective resistance. So if two nodes are farther away, then they are going to have less influence with each other. So the Jacobian abstraction is going to be higher. And if we just think about this for all the nodes in the graph, not the Jacobian abstraction, but the sensitivity for all the nodes in the graph, it's also bounded by the effective resistance, the total effective resistance. So we compute the sensitivity between pairs of nodes in the whole graph, and we sum up for the whole graph. It's bounded by the total effective resistance, which is, if you remind, the sum of all the pairwise effective resistance between nodes. So the larger the total effective resistance is, the lower the sensitivity between nodes. And of course, there has been proposed a lot of solutions here. I will go faster. I will just mention some of them, but I invite you to go through the presentation. So the first one is graph rewiring. Graph rewiring literally means change the edges of the graph and then perform the message passing function on this new set of edges with the idea of connecting long distance nodes, reduce the bottlenecks, and increase the sensitivity. It can be spatial or spectral. The idea is that we use different strategies based on different metrics. Spatial takes into account more the local neighborhood, so it takes the k-hops. And spectral is based more in these measures that we commented about global features. And both of them actually reduce the effective resistance of the graph, and that's why then the upper bound of the previous Jacobian is improved. But they do it in a different way, of course. Then can be static versus dynamic. Let's say that I can have a different rewired graph for each different layer of the GNN, and I can do it in a preprocessing step, like, okay, the heuristic is preprocess. I know how it's going to be the rewiring even before or at each layer, or we can learn the rewiring somehow. So that's the idea, that the spatial versus spectral. And the spatial one, you preserve more the locality information, so the inductive bias that Ameya was talking before, but you need to rewire a lot because as it's based in more local changes to connect the whole graph, you have to connect more. And then in the other hand, you have the spectral way, which is you preserve the sparsity because you don't need to add that many nodes to connect everything, but you lose this inductive bias, this locality information. And there are some approaches, spatial, spectral, and a couple of them spatial-spectral. And that's kind of the idea of the rewiring. This is like the total effective resistance of the graph. Okay, it seems that the spectral works way better, but then you might be losing all this spatial information in your graph. I will go fast. We can measure with curvature. There's a big line of works in curvature. So you can think about spheres, Euclidean and hyperbolic spaces in terms of positive, neutral, or negative curvature. And actually, the graph counterparts are these. Positive curvatures are more connected graphs, and less connected graphs have negative curvature. So the idea is to increase the curvature in the graph. So the idea is we identify the edges with low curvature and we add edges around them, so we reduce the curvature of the graph. Also, one spectral rewiring approach that we presented at Log a couple of years ago with Ahmed, Francisco, and Nuria. The idea is to learn, Ameya has talked about the resistive embedding, which is the commute times embedding. It's an embedding of the nodes that the Euclidean distance is the commute times, is the effective resistance, actually, of the graph. So the idea is basically that we can learn that rather than pre-compute it and put it in the message passing layer as node features. The idea is to create a GNN layer that learns that. So the idea is that the commute times is also a solution to a minimization problem, which is this Z equal to arc mean of this Z transposed Dirichlet energy, blah, 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 blah. And we transpose it into a loss function. So the idea is that with loss function, we can learn a kind of commute embedding during the GNNs of the graph, so during the layer of the GNNs of the graph. Once you learn that, you can use it as a diffusion matrix, as features, nothing else. And it improves graph classification, and depending on if you use it as a diffusion and you connect distance node or you put positional encodings, you improve heterophily or homophily. And these two approaches, the previous ones, the curvature and the effective resistance, some paper of the Bryan-Lambiot, they are connected. Actually, the no curvature and effective resistances are connected by these two, by these two curvature functions. Okay, and yeah, there's more spectral rewiring. I just mentioned you can just estimate the change of the spectral gap and do some kind of operation and rewiring operation that increase the spectral gap in a preprocessing manner. Also the work by Black et al., they actually compute how much the total effective resistance changes after adding one edge. And they add the edge that most reduces the total effective resistance. This is an example of adding by spatial methods like curvature methods and GTR in the total effective resistance as before. We also have dynamic rewiring. The idea here is to highlight some kind of dynamic rewiring, that rather than having one rewired graph on each layer of the graph, we do message passing based on one different graph. The idea is that you connect in the first layer, you do normal message passing. In the second layer, you connect the nodes that are at 2 hop, in the third layer at 3 hop. And you can do it on the same graph, so let's say on the same embeddings, or you can do it even on previous embeddings. It's some kind of more that you also identify when you have to combine the features rather than only if the features are combined. And there are also approaches that they do a spatiospectral to try to preserve sparsity and preserve the locality. So the idea is you have some kind of spectral metric and some kind of spatial metric, and you rewire it based on some limit. You put limits on these rewirings. Okay, I'm not gonna be very local, but I'm not gonna be very spectral. Yeah, you can think also about the other architectures, transformers, or even multi-hop and high-order GNNs as a kind of rewiring, but that goes beyond that. And some problems is that it's blind to downstream task. Usually we're just rewiring, hoping to increase the Chigir constant or the metric, so they are not task agnostic. They are task agnostic and usually are not learnable. Other approaches are virtual nodes that they solve over squashing. We add a virtual node, and the idea is that it creates like a shortcut in the graph and connects, and it serves as a shortcut for the information. And it works for a couple of things by the work of Southern et al. They basically, in the left part, they show that for most of the graphs, the average commute time between nodes is reduced when you add a virtual node. So you're reducing the effective resistance in most of the graphs. And also you are increasing the sensitivity. If you are more than 2 hops away, you are going to have a shortcut by your virtual node, as long as you have a mean aggregation function, but yeah, you can take a look at the paper. And then some advanced architectures, as we see this work by Velingker et al., they learn when and how they have to combine the features by a differentiable message filter mechanism for each different layer. And they also learn which is the optimal depth of the network, which I find very interesting. Using variational inference, you assign a kind of prior to the depths of your network, and you learn, during the learning process, you learn if these two, you learn the depth of the graph. Yeah, so basically this over-squashing is caused by the bottlenecks in the graph and the long range, and you can do rewiring virtual nodes, etc. I'm going to skip this part, basically, but maybe you have already realized that there's a trade-off here. Because basically the over-squashing, the more connectivity in the graph, the more over-smoothing is, but the less over-squashing, and the other way around. And you can look at that, the lower the spectral graph, the more over-squashing, and the other way around for over-smoothing. Same with effective resistances. If the effective resistances are smaller, the more over-smoothing, but the more over-squashing. So yeah, it's a kind of trade-off, and yeah, if we rewire a graph, we have one problem. If we sparsify it, we have the other. And this is, you can look it theoretically in the Giraldo paper, but the higher the bottleneck, the lower the mixing steps. So yeah, if you want to increase the spectral gap, you have to reduce the bottlenecks. Yeah. And these are just some works that we will share that they highlight and they analyze this kind of trade-off. So yeah, before we finish, we're a bit ahead of time, but some open questions that I find interesting, and I think that some people that I talk in the community, they also find interesting, is that first on over-smoothing, practically, as I said, is very fragile, this phenomenon. As long as you put some kind of machine learning thing or you modify the dynamics, it happens or not happens, or you have good or bad accuracy, no matter the over-squashing. So there's some work that they say, okay, even some kind of smoothing is okay if the smoothing happens in the same direction as your features in the graph. Let's say that over-smoothing happens at different rates on different parts of the network, and if these different parts of the network are aligned with the features, with the labels, it's kind of good over-smoothing. They call the paper not too little, not too much. Also for over-squashing, there's some kind of metric. So for instance, we rewire like this, we connect everyone to the bottleneck, and both the upper bound for the bottleneck and sensitivity is reduced, total effective resistance. So we see that the average effective resistance per node is reduced. But actually, which is the first chart there, but if we look at the normalized effective resistance, is more extreme. There is one node that it's more bottleneck. And you see this in the curvature in the third graph. Actually, the bottleneckness or the node curvature for the central node is way higher than before. And by those other two metrics, you actually could say that you are improving it. And yeah, that's something that with classical metric like between us, you don't see because nothing changes here. The shortest path distances doesn't change. Another question is that, as I said before, we are measuring sometimes, we are confining to measure long-range things with heterophilic metrics. And here 2 examples of one graph that is very homophilic, the line graph. But there is one long-range interaction, which is the 2 green nodes. They should interact, and they are very long-range, but the homophily is almost 1 if you increase this line. And the other way around, in a bipartite graph, the homophily is 0, but the maximum distance between 2 nodes of the same label is 2. So yeah, there are different approaches that they try to, here some works, that they try to propose new homophily metrics to try to capture how the features are spread out in the graph. And one last question that I would like to say, okay, before the last questions, I think just to wrap up the eigenvector language that we were talking about, the idea is that if the signal is smooth over the features are smooth over the graph, they correlate with low eigenvectors, and if the feature signal is sharpened over the graph, so more structural heterophilic, it will correlate more with higher eigenvectors, and it was shown here. And the last thing I would like to just mention is just this a personal point of view maybe is when we try to do inference, usually machine learning, we try to measure the probability of some features, some labels, some other random variables that we have. And I think that for measuring this kind of problems, measuring the probability distribution of the graph, how, still I don't know, could be a potential, good potential line to understand this problem. So I'm very interested in this problem, and you can just understand the independency between these random variables and ask questions like if the structure is helpful or not. And this thing has already been looked into deep graph generation, graph structure learning, and some works on causality and GNNs. So yeah, basically the conclusion is that you have over-smoothing, which is all features collapse. We have over-squashing, which is like there is a bottleneck and the features are not sensitive to each other. And the open questions are like that usually they are not task-oriented, and what we have mentioned before about measuring properly the long range. So yeah, there is more recent work in these two GitHub repositories. Very nice, and thank you to the author because it gathers all the works. And yeah, also there's in the community of graphs, there is also one conference that the submission is in a couple of months. So if you're interested in learning on graphs. And yeah, that's all from our side. Here are the references. I think this has opened more questions than solve it, because I think GNNs is a very live field. This is the the web page. And yeah, we want to thank about a lot of course, all collaborations of all the papers. You can check them, but on top of that, a lot of people that we have been talking during last years about over-squashing, over-smoothing, expressivity, and generalizability. Yeah, as we are a bit ahead of time, with no further ado, we are gonna move to the panel discussion. So I hope you enjoyed the tutorial, and yeah, invite the speakers in the hall to join the stage.
All right. Yeah, thanks for joining us. So from left to right there, we have, I think, Bryan Perozzi, research scientist at Google Research, then Michael Bronstein, DeepMind professor of artificial intelligence, and finally Christopher Morris, who is at Aachen University. And we also have a special guest, Michael Galkin, who is joining remotely. He's a research scientist at Intel Labs. He couldn't make it due to visa troubles, but has graciously accepted our invitation. So thank you. Okay, so I guess I'll start with the question, and we'll try to hopefully have some interesting discussion. But in terms of the area of graph learning or machine learning and graphs, what would you say are kind of the big questions to solve? What are the future directions? And I know that Christopher and Michael Bronstein, that is, authored a position paper that came out a few months ago that was talking a bit about future directions. So it would be interesting to hear your perspectives specifically on this.
Yeah, so I think with regard to the future of graph learning, so I have more of a theoretical background, and you learned about this connection between MPNNs and 1WL. I think this was very good to understand the ultimate limitations of MPNNs, but I believe we need some more fine-grained understanding of expressivity. Right, so this 1WL graph isomorphism perspective is in some sense binary, right? So it only tells you if two graphs are distinguished or if they're not. So it only tells you if two graphs are close or if they're very far apart. And hence I believe we need some more nuanced notion of expressivity. And in terms of generalization, I think not much is understood. So the current generalization bounds, for example, the ones that Ameya proposed, they're very coarse-grained, and they don't have any practical implications. So they don't really help practitioners to choose a model or something like this. And in terms of optimization, I think there's even less theoretical understanding. So we have only very preliminary analysis that make very simplifying assumptions. Right? So for example, answering questions, when do GNNs optimize with stochastic gradient descent converge to a global optimum if all the activation functions are linear. And of course, this is not something that we do in practice. So I think we really need to align theory and practice more closer together.
I can go next. So another topic that at least we've been working on quite extensively in the past couple of years, in particular with Francesco Di Giovanni, who his name I think was one of the most common words in this tutorial. Basically seeing analogy between continuous models, so in particular differential equations, PDEs, and graph neural networks, which you can show could be considered as discretization of continuous systems. And you can derive some smart, educated architectural choices for this purpose. For example, we showed that if you regard convolutional neural networks, graph convolutional neural networks, as gradient flows of some parametric energy, it basically gives you kind of disciplined way of choosing your architecture, and you can show certain things, again, that like what has been mentioned in the tutorial, for example, that you can probably avoid over-smoothing with the right choices. So graph rewiring can also be considered from this perspective. Basically, it's just some form of discretization of a continuous object. So to me, at least, this is an interesting perspective. We can potentially connect it also to optimal control theory and other maybe more exotic topics such as algebraic topology and differential geometry.
Yeah, so from a slightly different perspective, I think in industry, the thing that matters most is always, do you have the right graph? So all the work, I think kind of recent interest in graph rewiring or finding the optimal graph for a problem, we've been working on that for a long time, and it's exciting to see more people caring about it. Because if you don't have a good graph inductive bias, your graph algorithm will not help you, right? And so why even bother? The other thing that's, I think, very interesting, right, obviously the foundation model AI thing, and the intersection of that with graph algorithms and structured data is something that we've been working on very closely for the last couple of years. And so I think it's really, the questions we're trying to answer are things like, when is the right time to use a graph algorithm? When is the right time to use a more general foundation model? And, how the fusion combination of them, is best done for particular applications. We got Mike? No.
Michael Galkin.
Yeah, I can hear you. Yeah. To me, I would support Bryan here in saying that foundation models seem to be very interesting, especially in terms of generalizing across several tasks. Right now, it's pretty much impossible having a single model which would do, say, node classification or link prediction. And one of the biggest problems there is to devise a proper pre-training algorithm, because for quite some time, there hasn't been an effective pre-training algorithm that would actually be bringing significant gains over just running training vanilla GNN over your data set. So, I would say first, the big thing would be foundation models, graph foundation models. The second one would be how to elicit pre-trained knowledge to those prediction tests.
Yeah, so actually I wanted to ask you a follow-up question. So I think, Michael, you had you also had a position paper that came out a few months ago on, I think the title was something like Graph Foundation Models Are Here. So yes. Can you say a little bit about why you think we need graph foundational models? Why do we need something that's kind of general that works across different domains? Why not have specific models? And how much success have we seen with graph foundation models?
Yes, indeed. Thanks for highlighting that. There is a spotlight position paper which was presented during the main conference called Graph Foundation Models Are Already Here. And indeed, what we have found is has been different trends spanning from actually quite different areas in the literature. First, from geometric deep learning, where we already have those, say, neural network potentials. They predict essentially regressors over various graph structures. Then there is a good bunch of literature more in enterprise world on classification and link prediction. And over the years, we have accumulated actually quite a solid understanding of things to be done to devise those foundation models. But so far, there are only very few actual working models that would generalize it to all graphs across link prediction or to all graphs for non-classification. So yeah, that will be a nice segue to maybe highlighting. We have recently written a blog post with Michael Bronstein on that, which I would invite everyone to read as well. Yeah.
If you can make.
I mean, Michael, I mean, I really like the idea of graph foundation models, but I still don't understand why should they work. I mean, why is it a good idea to train a single model for multiple distributions, let's say it like this?
Yeah, because generally the idea is that showing more data and showing more tasks will make the models more capable, as shown by vision models and language models who have been trained, who can be trained on many tasks, like segmentation, masking, and so on. And the same applies for tasks in language. And we have seen cross-pollination across those areas, across those tasks to models that can do several tasks, generally better. So we haven't seen right now that in graph models because graph models are small. They are harder to train at scale because hardware is less friendly to that. But the hypothesis is, and well, we have some first evidence that generalized models can show even better performance when they can do, say, both classification and link prediction. Especially when a lot of those tasks can be trained as one of those. So for instance, classification is easily trained as link prediction, and vice versa.
So you're saying because it worked on, let's say, vision tasks, it should also work in graph tasks. That's kind of the hope.
With a belief in deep learning. Yeah, with large over-parameterized models and large pre-training data sets, it is likely to work. The problem is that we don't have large graph data sets and we don't have large graph models yet to pre-train.
So if I can add to this, so the appeal of foundation models for graphs is that basically they will learn some kind of generalizable rules, local rules on graphs that could be applied to different graphs. Unlike foundation models in language processing and vision, you don't even have a shared vocabulary in graphs, right? So in language, more or less any language, we can think of it as a collection of tokens, right? So maybe the vocabulary is very large, but still there are basic units that are well defined. Same thing in vision, for example, in vision transformers, you can think of patches, right? So the images can be very different, but the patches are still the same patches. In graphs, we deal with situations when the graphs can come in all forms and flavors. So you might have graphs with very different types of features and dimensions of features and class labels. And maybe you have also some features on the edges of the graph. So even the types of the problems that we deal with, sometimes they have completely different vocabulary and completely different way of thinking about them. So there have been some foundation models in certain situations, but as Michael mentioned, there are no currently, at least we are not aware of any model that can solve all sorts of graph learning tasks in different situations.
Let me jump in here too. Yeah, I'm going to jump in too. So I'd like to conjecture that general foundation models are already graph foundation models, which may be what you said in the paper, because I apologize, I didn't read it. But if not, then I think that's my take here. Not that they're the best at graph tasks, but I mean, you can measure how well they do on graph tasks. They're getting better at graph tasks over time. In the last year, larger and more capable models are even better at graph tasks than they were previously. I mean, it's, you know, they're still not perfect, but it's you know, obvious that work on mathematical reasoning and other areas that the language community is focusing on is adding graph reasoning capability, in my opinion.
But maybe to counter conjecture this, I would say that LLMs are not necessarily the best architecture for reasoning on graphs, right? So one issue is scalability. So graphs can be gigantic, and I don't think that LLMs can work with, I don't know, billions of tokens, right? So at least we haven't seen them yet perform at this scale. And second, basically by massaging the graph into an LLM, you inherently break its structure. So in my view, foundation models for graphs still should be based on some form of message passing, maybe adopt some techniques from LLMs for these tasks.
So Bryan, talking about conjectures, right?
Hey, that's the whole point,
do you
right?
think graph foundation models will eventually replace specialized models like GNNs or graph transformers?
So I hate to disagree with you here, Chris, but I think that there's a future here, right? I mean, I'm not saying that we're at the future today, but I am saying that I've wasted a lot of time training one-off models, like a lot of time of my life that I wish I could get back. And when I look at all these people out there, they want that time. And because they want that time, they are going to find a way to spend less time training, right? So better pre-training. I mean, here's another conjecture. You guys want some wild takes? Deepwalk is a graph foundation model, but so is PageRank. Right? These are simple models that like allow you to do simple things. They can do node classification. They can do link prediction to some extent, and making this kind of pre-trained model better has immense industrial applications. And people will get to something. Now, what that something is, who knows, right? But I do think that there will be more off-the-shelf models available. And I think we've actually had the capability to do it for a while. We just didn't think about doing it because we were, busy doing graph stuff, and we weren't just thinking about multitask training. We just weren't focusing on it. I think if the community focuses on it, we're going to see some interesting things happen.
But why do you think that multitask training actually helps?
I believe that for some in-domain, let's call them in-domain graphs, like the citation networks, which GNNs were unfortunately evaluated on for a long time. I am 100% sure you can learn something from one citation network and transfer it.
Oh, okay, I agree with this. But for example, if you train on like chemical molecules, and then you want to use it downstream for citation networks, we agree that this is probably not a good idea, or is it a good idea?
Well, I don't think it's a good idea, but I do think that there's, I think it would be possible to make a model. I think it's definitely possible to make a model cover different modalities, similar to how you can translate between languages in a language model. The structure of German and the structure of English, some similarities. The structure of Hungarian and English, maybe less similarities. But you can have a model that can relate between these things. So we know we have models that have the capability to capture different distributional effects, and I think, is there a commercial advantage to figuring out how to relate information from citation networks to molecules? I think so, because people write papers about molecules, and there's some need to translate between these things. I'm not saying it's straightforward, and I'm not saying it's the best use of a graph, but I think there's advantages here.
Yeah, I would perhaps add that actually there is a direct link between link prediction, citation networks, and molecules, and it's just triangle counting and substructure counting. So a lot of properties of those graphs, say molecules, there is another unfortunate benchmark on which many graph transformers noted, which is zinc, and zinc is synthetic benchmark, where you can get the best number by enumerating very well substructures, high-order structures, triangles, simple shell complexes, and so on. And this is the same that applies for link prediction. So link prediction is essentially triangle counting. So if you are able to efficiently capture several substructures, then you will be able to transfer this knowledge to link prediction. And those seem to be very different areas in first glance.
Yeah. Thank you very much. Unfortunately, we're running out of time, so I would like to ask you for 1-2 sentences for wrap up in this last interesting topic that you brought. So why graphs can be the models that will be able to generalize over this structure and not LLMs in this case. You brought up something like scalability and that you break the inductive biases, but I would like a couple of sentences in this line against or in pro.
Or just to add to that, right? A common question that we often get is, isn't everything LLMs nowadays? Why should we even study this? Just keep your answers short because we're running out of time, but just if we could summarize.
Well, to be honest, I haven't seen any work
kind of tries to feed in a graph or does graph learning with LLMs that was convincing.
Oh, you should see my papers.
I think Bryan might
maybe you
have
should
some interesting
your
counter.
papers, but
We also had a paper.
Let's talk after this.
Okay, I will read you guys' papers, but I think there's a lot of work that has to be done. And it's not really clear if this is actually a good direction, in my personal opinion.
So, well, I think there are two components to this. So first of all, whether transformers that are used in LLMs are a form of GNN. So whether everything looks like a graph, I think, at least from a mathematical perspective, we can argue it, right, at least in some cases. Whether you need to implement GNNs, I think here that it's more pragmatic consideration, what is called hardware lottery. So when your graph is sufficiently dense, then it makes no sense on at least modern GPUs to do anything that is more sophisticated than a transformer. Basically, all computationally, there will be no advantage whatsoever. So in some sense, transformers are a happy marriage between the hardware architecture that NVIDIA has been pushing to us and certain algorithms. Now, regarding LLMs and graph neural networks, so you can try to incorporate some graph structure into LLMs, and this has been done, I think, with variable success. There have been a few interesting works recently. I think one was done by Pratyusha Sharma from MIT. Another one, the opposite direction is basically whether you can think of graphs and shove them into LLMs. So, well, Bryan, you've done this, we've done this. So while it's very appealing, basically you have zero-shot generalization to previously unseen graphs, very different distributions. Again, as I mentioned, I don't think that this necessarily is the right computational architecture for dealing with graphs.
Galkin?
Yeah, just in brief, I think this is a great time to be working in this area. There's been a lot of interest in graphs over the last 5 years, but right now it's actually probably a lot easier to get a paper published in graphs than it was maybe 2 years ago when there were way too many of them. So I also, practically speaking, I'd encourage everybody to keep the faith, and graphs. But the other thing is that I think, there are so many applications for graphs to help in efficiency, right? We have work that shows that you can take a tiny GNN and make your LLM way better at solving graph problems. I think that, the practical applications and the business justifications for graph stuff is still there, right? We still have big data, we still want to have scalable decompositions, and we still would like efficient algorithms. And this is what graphs bring to the table, 100%. So I encourage you all to go home and think about the coolest thing you can do with graphs.
Yeah, Michael Galkin?
Perhaps, yes, I would perhaps add a word about two augmented language models. I think that there is quite some potential if LLMs, foundation models, frontier models use graph modules as external components. This has shown quite some impact in AI for science and automated chemistry and material discovery pipelines. When LLMs do not know much about materials or chemistry, they just call the stored module, and it is doing formulating some graph tasks and performing graph tasks in the background, and then spitting out the result, which is then accumulated by LLMs and then processed further. So some intersection in the interleaving of those external models, I think that is promising.
Yeah. So, thank you very much, all of you, for this interesting discussion. Please join me to thank all of the speakers in this panel session for being here. We wrap up the tutorial here. So if you have further questions, just contact us. Slides will be on the webpage soon. Thank you very much for attending the tutorial.